Imagine the universe isn't just this endless expanse, but something much stranger, something that might actually be inside a black hole. It sounds wild, but there's a surprising coincidence in physics that points exactly in this direction. When scientists calculate the mass of everything we can see, the observable universe, and then figure out how big a black hole would be if it contained that same amount of mass, the size they get matches almost perfectly with the age of the universe expressed in light years. Even more surprisingly, this same number shows up when measuring how fast the universe is expanding. This overlap isn't just a fluke, it hints that maybe the universe isn't outside a black hole, but inside one. To grasp why this is so important, we have to rewind back to 1915 and Albert Einstein's revolutionary general theory of relativity. Einstein didn't think of gravity as a pull or a force like Newton did. Instead, he explained gravity as the bending, or warping, of space and time, space-time itself, caused by mass and energy. Massive objects like stars and planets curve the fabric of space-time around them, and this curvature is what we experience as gravity. Einstein's field equations, which describe this bending, were notoriously tough to solve. Even Einstein struggled to find exact answers. But then, during World War I, a German astronomer named Karl Schwarzschild, while serving on the Russian front, found a precise solution. Imagine being in the trenches and discovering this. It's remarkable. Schwarzschild's solution described the shape of space-time around a simple, non-spinning spherical mass. And hidden in his math was a critical radius, the Schwarzschild radius. If you squeezed any mass into a sphere smaller than this radius, space-time would behave in a bizarre way. Time would slow down at the boundary, and light wouldn't be able to escape. The object inside would become what we now call a black hole. For perspective, the Sun's Schwarzschild radius is about 3 kilometers, while the Sun itself is nearly 700,000 kilometers wide, so it's nowhere near a black hole. Earth's Schwarzschild radius is roughly 9 millimeters, and the Moon's is a fraction of a millimeter. This radius grows directly with mass, double the mass, double the radius. Here's the twist. Because volume scales with the radius cubed, as black holes get bigger, their average density actually drops. A black hole the size of a collapsed star is insanely dense. But supermassive black holes, millions or billions of times the Sun's mass, can have average densities as low as water or even air when spread across their vast event horizons. Now, turning back to the universe, the observable universe stretches roughly 46.5 billion light-years in radius if you account for the expansion of space over time. Even though the universe is about 13.8 billion years old, the expansion means that objects we see from the early universe are much farther away than the straightforward light travel time suggests. By combining the critical density needed for a flat universe, which cosmologists estimate from the cosmic microwave background, galaxy distributions, and expansion rates, and the volume of the observable universe, scientists get a total mass around 7.7 times 10 to the 53 kilograms. Some estimates vary a bit depending on if you include only ordinary matter or also dark matter and dark energy, but the numbers are close. Applying Schwarzschild's formula to this mass gives a radius about 13.7 billion light-years, which aligns astonishingly with the Hubble radius, the distance light can travel divided by the universe's expansion rate, about 14 billion light-years. This was first pointed out by physicist Raj Pathria back in 1972. He noticed the universe's structure resembles the inside of a black hole. Both have singularities, one in the past, the Big Bang, and one in the future, the black hole's central point of infinite density. Both have horizons beyond which nothing can pass, our cosmological horizon and a black hole's event horizon. But this is more than a coincidence. The equations governing the universe's expansion, developed by Alexander Friedmann in the 1920s based on Einstein's relativity, show this connection mathematically. Friedmann's equation relates how fast the universe expands, the Hubble parameter, to its density, spatial curvature, and cosmological constant. When the universe is spatially flat, meaning zero curvature, the critical density is directly tied to the Hubble parameter. If you imagine a sphere with a radius equal to the Hubble length and fill it with matter at the critical density, The Schwarzschild radius for that mass matches the Hubble length exactly. This isn't a random overlap, it's baked into the math of spacetime itself. So, does this mean the universe is literally inside a black hole? In 1939, J. Robert Oppenheimer and Hartland Snyder explored what happens when a uniform cloud of dust collapses under gravity. Their simplified model showed that, from the outside, the cloud would collapse and form an event horizon, the boundary of a black hole. But from the inside, space remains homogeneous and locally flat until matter compresses near the center. Interestingly, the interior of this collapsing cloud can be described by the same Friedmann equations that describe our expanding universe, but in reverse, as a collapse instead of an expansion. Flip this around, and you get a mind-bending idea. The inside of a collapsing black hole, running backward in time, looks like an expanding universe. The singularity at the center, where everything falls in, becomes the Big Bang singularity, where everything emerges. This was the core insight behind Pathria's black hole cosmology hypothesis. He suggested that our universe could be the interior of a black hole that formed inside a larger, parent universe. From our perspective, space expands smoothly, but from an outside vantage point, it looks like a black hole. Taking this further, the concept of a white hole, the theoretical reverse of a black hole, enters the picture. While a black hole traps everything inside, a white hole would spew out matter and light, but nothing could enter it. Though white holes remain purely theoretical with no observational evidence, in black hole cosmology, the Big Bang singularity might behave like a white hole, representing a boundary from which our universe emerged, invisible and unreachable from outside. In 1999, Stephen Hawking showed that under certain conditions, the distinction between black holes and white holes can blur. If a black hole perfectly balances the radiation it absorbs and emits, the event horizon becomes fuzzy, suggesting that the question of whether our universe is inside a black hole or a white hole may be meaningless. The inside spacetime would look the same either way. However, singularities remain a thorny problem. They represent points where density and curvature become infinite, and physics as we know it breaks down. To fix this, physicists have looked for extensions to Einstein's theory, like Einstein-Cartan theory, introduced by Elia Cartan in 1921. Unlike Einstein's model, where spacetime has curvature but no torsion, Einstein-Cartan includes torsion, a twisting of spacetime that arises from the intrinsic spin of particles like electrons, quarks, and neutrinos. In the mid-1960s, Dennis Sciama and Tom Kibble showed that this torsion acts like a repulsive force at extremely high densities, counteracting gravitational collapse. While negligible at everyday densities, even inside neutron stars, torsion becomes crucial at near-Planck scale densities, preventing singularities. Instead of collapsing infinitely, matter would reach a smallest size and then bounce back. A big bounce, replacing the problematic singularity with a smooth transition. In the 2010s, physicist Nikodem Poplawski applied Einstein-Cartan theory to black holes. He demonstrated that torsion would stop the formation of a singularity inside a black hole. Instead, matter would compress to a finite density, bounce, and then expand into a new region of spacetime beyond the event horizon, a new, closed universe. From inside, this would look like our own expanding cosmos, but from the outside, it's just a black hole. According to this model, every black hole potentially creates a new universe. This idea opens the door to a cosmic family tree. Our universe could be just one in an infinite chain of universes, each birthed by a black hole in its parent universe. Theoretical physicist Lee Smolin proposed in the 1990s that this process might even be subject to natural selection. If physical constants in daughter universes vary slightly, those universes producing more black holes would have more offspring. Over countless generations, the multiverse would evolve to favor constants that maximize black hole formation. This could explain why our universe's physical constants, like the strength of the strong nuclear force, electromagnetic coupling, and the proton-to-electron mass ratio, seem so finely tuned to support star formation and black hole production. Alternatively, some researchers, including Poplawski himself, suggest daughter universes inherit the exact same constants as their parents, without mutation. In this view, the multiverse is simply reproducing, not evolving, avoiding the puzzle of how constants might change at singularities if torsion removes them entirely. Either way, the implications are staggering. Humanity might be living inside a black hole, part of an endless cosmic lineage stretching across an infinite multiverse. Is there any way to test this? One place to look is the so-called Hubble tension, where two methods of measuring the universe's expansion rate don't quite agree. One method uses the cosmic microwave background, the relic radiation from the Big Bang, while the other measures more local distances. Understanding these discrepancies might provide clues about the universe's true nature and whether it's linked to black hole cosmology. The universe might be far stranger than anyone ever imagined. What if the universe we live in was actually born inside a black hole? This mind-bending idea might sound like science fiction, but it's a serious hypothesis that could explain some of the biggest puzzles in cosmology. One key mystery is the mismatch in measurements of how fast the universe is expanding. Scientists use two main techniques. One looks at the cosmic microwave background, the afterglow of the Big Bang, and the other observes distant exploding stars called supernovae. Surprisingly, these two methods disagree by about 10%, a gap that stubbornly remains despite ever more precise data. Some researchers think black hole cosmology could bridge this gap. If our universe's expansion is influenced by the growth or properties of a parent black hole, the rate of expansion might shift in ways that current cosmological models don't account for. Another intriguing clue lies in the cosmic microwave background, which is mostly uniform but contains tiny variations that seeded galaxy formation. These fluctuations should be random, but scientists have noticed odd large-scale patterns. One is called the axis of evil, an unexpected alignment in the cosmic microwave background's quadrupole and octupole moments that points in a specific direction in space, something not predicted by a universe that should look the same in every direction. There's also a hemispherical asymmetry, where one half of the sky exhibits slightly stronger fluctuations than the other. Some black hole cosmology models, especially those involving spinning or rotating black holes, suggest these anomalies could arise from the spin of the parent black hole. The rotation would create a preferred axis, imprinting a kind of cosmic fingerprint on the daughter universe. Physicist Poplawski has argued that these features might be the signature of our universe's birth inside a rotating black hole. Then there's the baffling discovery of massive galaxies and supermassive black holes in the universe's infancy. Observations from the James Webb Space Telescope have revealed these enormous structures existing when the universe was less than 1 billion years old, far too soon according to traditional models of cosmic evolution. Standard cosmology struggles to explain how such huge objects could form so quickly after the Big Bang. However, certain black hole cosmology theories, which propose rapid structure formation triggered by bounce mechanisms, may better fit these puzzling observations. Gravitational waves add another piece to this cosmic puzzle. Since 2015, detectors like LIGO and Virgo have picked up ripples in spacetime from merging black holes. By studying the masses and merger rates, scientists can infer details about black hole populations. If the universe is optimized for black hole production, a concept known as cosmological natural selection, patterns might emerge in these data. So far, the results align with standard formation scenarios, but they don't rule out alternative explanations involving black hole cosmology. Another fascinating hint comes from galaxy spin directions. Research led by Lur Shamir analyzed the rotations of over 200,000 galaxies and found a slight but statistically significant asymmetry. A tiny majority rotate one way over the other, especially at great distances. Though subtle, about 51 to 49%, this imbalance could suggest the universe itself has a net rotation, potentially inherited from a parent black hole. None of these clues alone definitively prove black hole cosmology, and each has competing explanations. But together, they keep the idea alive as a serious contender for understanding the universe's true nature. This theory might also resolve a long-standing paradox in physics, the black hole information paradox. In the 1970s, Stephen Hawking showed that black holes emit radiation, now called Hawking radiation, as a quantum effect near their event horizons. Over time, This radiation causes black holes to lose mass and eventually evaporate entirely. The problem is, Hawking calculated that this radiation is purely thermal and random, carrying no information about what fell into the black hole. This clashes with the core principle of quantum mechanics. Information cannot be destroyed. For decades, physicists have wrestled with whether information truly disappears inside black holes or if some mechanism preserves it. Black hole cosmology offers a neat solution. If the inside of a black hole becomes a new, separate universe, then the information isn't lost but passes through the event horizon into this daughter universe. It's preserved, just inaccessible from our side. This idea echoes the holographic principle, which says that all the information inside a black hole is encoded on its event horizon, but here, the information actually transfers to a new spacetime. This framework also gives insight into why time flows in one direction. The laws of physics are mostly time-symmetric. They work the same forward or backward, yet we experience a clear arrow of time, moving from past to future. Poplawski suggests that the one-way crossing of matter through a black hole's event horizon sets this directionality. Matter only moves inward, never back out, establishing a time arrow in the daughter universe. Entropy, or disorder, increases along this path, explaining the second law of thermodynamics. Meanwhile, the parent black hole continues to exist in its own universe, with the daughter universe forever beyond the event horizon, causally disconnected. When the black hole eventually evaporates through Hawking radiation, this cosmic connection is severed. The daughter universe detaches, becoming independent with its own space, time, and destiny. If our universe did emerge inside a black hole, the Big Bang would correspond to what's known as a white hole, a sort of time-reverse black hole where matter and energy emerge instead of collapsing. There should be exactly one white hole acting as the gateway to the parent universe. But because of the vast distances and the finite speed of light, we wouldn't see this white hole as it is now. We'd be looking back in time, perhaps seeing only early stages when matter was still flowing through. Poplawski has even proposed that matter from the parent universe could still be streaming into ours through this white hole, billions of years after the initial birth. If so, this might show up as unusual sources of energy or particles, possibly detectable in the cosmic microwave background, or the large-scale structure of the cosmos. However, this connection wouldn't last forever. As the parent black hole evaporates, the link weakens and ultimately disappears. From our perspective, this detachment would take an unimaginably long time due to extreme time dilation near the event horizon. Yet for the matter crossing inside, the process unfolds over a finite time span. This paints a strange picture. Our universe feels like a unique, stand-alone cosmos, but on a grander scale, it's just one among countless daughter universes, each born inside black holes, each evolving independently as part of a vast multiverse. Another profound puzzle arises from a curious fact about densities. The universe's average density is incredibly low, about 5 hydrogen atoms per cubic meter, yet its critical density matches the Schwarzschild radius for its total mass. In other words, the universe's size and mass relationship resembles that of a black hole. This seems paradoxical. How can something so diffuse act like a black hole? The answer lies in how density works locally versus globally. Locally, any point in space is far too sparse to collapse gravitationally. Stars, planets, galaxies, all are denser than the cosmic average. But when considering the entire observable universe, the total mass is enormous. Since the Schwarzschild radius scales with mass, a sufficiently large volume of even low-density matter can have a Schwarzschild radius bigger than itself. This is why supermassive black holes can have average densities lower than water or even air. A black hole with the mass of 1 billion suns might be less dense than the Earth's core, and one as massive as the observable universe would have a density less than the air we breathe. But a black hole isn't just about mass and size. It's about the structure of spacetime that traps everything inside an event horizon, from which nothing can escape. Our universe doesn't have such a boundary. Light travels freely in all directions, and distant galaxies are visible. So in the traditional sense, the universe is not a black hole. But mathematically, the observable universe could be the interior of a black hole, not the exterior. Inside an event horizon, the boundary is one way. You can't go back through it. It's a barrier in your past, not your future. This aligns with the Oppenheimer-Snyder solution describing a collapsing cloud forming a black hole. Inside, space-time expands from the viewpoint of someone falling inward, with the singularity lying in the future. If torsion, a property related to spacetime's twisting, prevents singularities, the interior could expand forever, effectively creating a universe. Science demands testable predictions. So how can this black hole universe theory be tested? One route is to examine the cosmic microwave background for patterns hinting at apparent black hole's spin. Some anomalies fit this scenario, but none are definitive. Another is to analyze black hole populations in our universe. If cosmological natural selection is real, physical constants might be fine-tuned to maximize black hole production. Slight changes would reduce black hole numbers. Some studies support this, but it's tricky to pin down. Gravitational waves offer another avenue. If black holes spawn new universes, merger events might show subtle deviations from standard models, perhaps from quantum effects near event horizons. Future detectors like LISA could detect these fingerprints. Searching for quantum gravity effects is also key. Torsion should become important only at densities near the Planck scale, unreachable by current experiments, but it might influence particle physics or cosmological observations indirectly. Finally, the fate of the universe comes into question. When the parent black hole evaporates, the daughter universe would detach and continue on its own. This event is practically impossible to observe due to the vast timescales involved, but the theory provides a consistent picture of cosmic evolution. If the universe is inside a black hole, what does that mean for physics? Locally, nothing changes. The laws of physics remain as they are in any expanding universe. The event horizon surrounding us, somewhere beyond, doesn't affect particle interactions or space-time behavior here. But conceptually, it shifts the view of cosmic origins. The Big Bang isn't the absolute beginning but a transition from one universe to the next. Our universe isn't unique but one of an infinite chain of universes, each born inside black holes. This also reframes the fine-tuning problem. Instead of the anthropic principle, that constants have certain values because they allow life, black hole cosmology suggests constants are tuned to maximize black hole formation. Life happens to exist in universes optimized for black holes, not the other way around. This raises deep questions about causality and eternity. If every black hole births a new universe, and every universe creates black holes, does this chain go on forever? Is there a first universe or an original ancestor? Poplawski argues the cycle might be eternal, with no beginning or end, just an endless cosmic family tree of universes birthing universes. Imagine a cosmos where every black hole is not just a destructive pit, but a cosmic womb giving birth to entirely new universes. Some physicists propose this mind-bending idea, suggesting a never-ending family tree of universes, each emerging from the depths of black holes in a cycle with no true beginning or end. This concept sidesteps the classic problem of where everything started, but it also means accepting an infinite chain of creation stretching backwards and forwards without limit. Others, like theorist Smolin, envision the multiverse as an evolving ecosystem. In this scenario, universes that reproduce successfully spawn more offspring, hinting at a potential original universe where it all began. Yet, even that primeval universe begs a deeper explanation, pushing these questions into the realm where physics meets philosophy, territories still beyond the reach of current scientific tools. As of the year 2025, black hole cosmology remains on the fringes of mainstream physics. The reigning model is the familiar Big Bang theory, enhanced by inflation and neatly packaged within the lambda cold dark matter framework. This model has passed numerous observational tests and delivers precise predictions matched by data. Still, it struggles with its own set of puzzles: the Hubble tension, the elusive true nature of dark matter and dark energy, and oddities in the universe's large-scale structure that don't quite fit the standard story. Black hole cosmology offers a fresh lens to tackle some of these mysteries, but embracing it means accepting speculative ideas not yet confirmed, including the existence of space-time torsion, the replacement of singularities with smooth bounces, and the reality of a vast multiverse. Meanwhile, breakthroughs in string theory, particularly the ADS/CFT correspondence, suggest another way out of these dilemmas. According to this powerful framework, the infamous black hole information paradox can be resolved without calling on baby universes. Instead, the information swallowed by a black hole is subtly encoded in the Hawking radiation, preserved through quantum entanglement. This has become the go-to explanation among string theorists, though it doesn't clarify why the Schwarzschild radius of black holes and the Hubble radius of the universe so closely match. On a different front, loop quantum gravity offers its own insight. It predicts that the dreaded singularities at the heart of black holes are replaced by quantum bounces at the Planck scale. This supports the idea that singularities may never form, but it stops short of claiming that new universes necessarily sprout inside black holes. Recent advances in celestial holography, spearheaded by researchers like Andrew Stemminger, are pushing the boundaries further. They're exploring whether the holographic principle, a concept that encodes information about a volume of space on its boundary, can be extended beyond the strange anti-de Sitter spacetimes to the flat or de Sitter spaces that better describe our universe. This cutting-edge work could one day reveal whether our cosmos has a holographic nature, changing how quantum gravity is understood in a cosmological context. Meanwhile, astronomers are busy collecting data from every corner of the sky. The James Webb Space Telescope peers back to the universe's infancy with unprecedented clarity. Gravitational wave observatories continue to catalog black hole collisions, offering new clues about these enigmatic objects. Large-scale surveys map the cosmic web in exquisite detail. Each new observation sharpens the picture, narrowing down which theories hold water and which fall short. Yet many fundamental questions remain unanswered. Does torsion, a twist in spacetime predicted by Einstein-Cartan theory, really exist? Experiments at extreme densities, where torsion would matter most, have yet to deliver any proof. Are black hole singularities genuine or replaced by quantum bounces? Because all observations come from outside the event horizon, the interiors of black holes remain hidden from direct scrutiny. Gravitational waves might offer indirect hints someday, but their signals are subtle and hard to interpret. The fate of information swallowed by black holes is still unsettled. While the ADS/CFT correspondence offers a hopeful resolution, it applies only to specific spacetimes unlike our own. Whether its conclusions hold in the real universe's geometry is an open question. Is the universe infinite or finite? Current observations suggest a flat spatial geometry, consistent with infinite extent, but the cosmos could just as well be finite with a complex shape, like a four-dimensional sphere looping back on itself. If that's true, black hole cosmology models would need serious revision. The so-called Hubble tension, a mismatch in measurements of the universe's expansion rate, may indicate new physics, or could simply be a quirk of measurement. If real, it might relate to early universe dynamics or dark energy's true nature. Black hole cosmology is one possible explanation among many. Anomalies in the cosmic microwave background radiation raise further questions. Are these patterns statistically significant or just noise? Upcoming missions may provide clarity. Is our universe unique, or one bubble among countless others in a multiverse? This remains theoretical, with some multiverse concepts untestable in principle, sparking debates about what counts as science. And beyond the observable horizon? If the universe is infinite, it stretches endlessly. If finite, there could be edges or boundaries, but what lies beyond those is a profound mystery. Should we live inside a black hole universe, a parent cosmos exists beyond our cosmic event horizon, forever out of reach. These questions mark the cutting edge of cosmology, driving research forward. Some may find answers soon, others might linger indefinitely. The notion that the universe itself could be nestled inside a black hole is both bizarre and strangely intuitive. It doesn't change the night sky overhead, or the laws that govern everything from atoms to galaxies. From the inside, a universe spawned by a black hole would look no different than any other. Yet this idea shifts the way humanity thinks about the cosmos. It links the grandest cosmic structures, galaxies, clusters, the cosmic web, with the smallest, most extreme objects, black holes. It ties the Big Bang to the event horizon, suggesting the universe is not an isolated island, but part of a vast, interconnected multiverse. The mathematics describing black holes also apply to the universe itself. The underlying equations, the geometry, the peculiar coincidences, like the close match between the Schwarzschild radius of a black hole and the Hubble radius of the universe, or the similarity between the universe's age and the distance light has traveled, these are more than chance. They are clues woven into the fabric of space-time. Whether these hints point to a profound cosmic truth or are just elegant mathematical quirks remains unknown. The evidence is tantalizing but not definitive. The theory is elegant but remains unproven. For now, the mystery stands. Humanity watches from within, tracing the universe's history back to the earliest glimpses, measuring its expansion, composition, and destiny. Models are built, predictions tested, data gathered. The question lingers: are we alone in this cosmos, or one universe among countless others, each born from a black hole, each expanding into its own future? The answer, if it ever comes, will rewrite the story of existence itself. Yet even without a definitive reply, simply asking these questions highlights the universe's incredible depth, mystery, and interconnectedness. This is the wonder of science. Every discovery opens new doors, every answer sparks fresh mysteries. The more that is learned, the more it becomes clear how much remains unknown. All that remains is to observe, calculate, and wonder. The universe unfolds around us, immense, ancient, and filled with secrets. And hidden somewhere within the math that governs its structure, within those uncanny coincidences linking its traits, may lie the key, the sign that we don't just live in a universe, but inside one.